Well, good afternoon, everybody, and I've got to say it's a real pleasure to be here in the kind of hotbed of graphene development and now, of course, graphene commercialization, as we've been seeing from the talks we've had so far. It's pushed on a long way in the past 20 years. I mean, where's those 20 years gone? But we have come a long way in terms of what we've done with graphene, and this centre and the NGI have been a big part of that, so we should recognise that. So thank you for the opportunity to speak. Really appreciate it. So I'm going to change pace a little bit, and I'm going to start talking about what was one of the first kind of aims of graphene when it was first discovered or first isolated here in Manchester, which was around the electronic side of graphene. So it would be pretty ludicrous of me to start talking about the properties of graphene in this room, so I'm not going to. What I want to focus on is this electrical conductivity that the material has, or more accurately, the mobility that we have, the electron mobility that we have in graphene when it's in its pristine form. So when it was first created in the flake form, we saw this property whereby there was a glimpse into the potential that we could have if we could harness those electrical properties and put it into technology. And in fact, here and other places around the world, there have been technologies that have been provided, electronic technologies that show you what you can do in terms of enhanced performance and, of course, energy saving if you can get graphene into electronics. Now, graphene has a problem in electronics for certain applications because of its lack of band gap. It's a direct conductor. But actually, when you learn how to use the graphene and learn how to change its properties, it has incredible potential for not only giving better performing products, but also reducing energy consumption massively. And that's what I'll show you in the next few slides. Why is this important? Well, at the moment we use silicon technologies and compound semiconductor technologies to run most of what we do in electronics. And if you would like a highlight of why this is an issue, AI. The biggest thing being invested in the world today. Now, AI is a problem for this world. It's a solution and a problem. The problem is that in order to do AI, you require an incredible amount of energy. You've just seen the news yesterday of Google's increase in energy consumption, 48% increase in energy consumption, simply because they're switching to using AI searches as opposed to their standard search techniques. It astonished me when I read these facts. Data centers use more energy than the UK each year. We're looking at doing cryptocurrency, which has become a big thing for people now. Uses more energy than Argentina in a year. So we've got a real problem here, and materials can be the solution to this. And in particular, what I've just said about graphene, those electronic properties offer an opportunity for us to be able to fundamentally change the way in which we're using energy, i.e. reducing it. Problem is that graphene is not easy. Everyone in this room knows that. 20 years down the line, we still haven't built proper electronics from it because it's a really difficult material to work with. The challenge for us, the same way as it was for silicon and for compound semi years ago, is to be able to use that material in a compatible way with industry, to be able to integrate it with the infrastructure that exists that allows us then to build electronics out of that material. It's the same for every new material. You go through this barrier of how can we use it? How can the rest of the world use what we have? And then we can grow the proliferation of those materials. So that's our challenge right now in the graphene world. So, Paragraf. Our whole goal, the core of the company, is to deliver on that electronic promise. Is to take those properties that we know exist and convert them into a material that can be utilized by the whole of industry. So about 8 years ago now, we set about looking at methodologies to be able to create graphene in a way that industry would understand. So we have seen some wonderful inventions, some wonderful technologies using transferred graphene, and we still see them today. And it's fantastic what that technology has been able to produce. But what industry tells us is that that is not integratable with current semiconductor foundries. Now, there are some great technologies being invented to try and make transferred graphene integratable, But the reality is, why not try to remove that step? Why try to transfer something? Why not try to integrate the solution from the materials side? And that's what we've done at Paragraf. We've created a methodology, which we spun out of the University of Cambridge, where we can apply graphene, create graphene direct on substrate. So whether that's sapphire, silicon, silicon nitride, silicon carbide, in fact, now even on top of device structures, we can create graphene. So now you have wafers that have graphene on them that you can take and you can put into standard processing tools to make electronics. A missing link has now been filled. The methodology we use actually produces the best graphene in the world. Scaled graphene, that is. I'm not talking about flakes. Flakes have still got a very, very good set of pristine properties, but in terms of substrate-wise, the mobility, the purity of the graphene we make now is 5 times better than transferred graphene. And we are only just getting started. So as you can see here, we have completely perfect lattices of graphene. We have wafer-scale graphene. We have no defects, no inclusions. And what actually happens is when you get to this point and you start making devices, all of a sudden you can harvest those properties. So you can create sensors that have ultra-high sensitivity. You can create devices because of the way the graphene electronic structure is set up. You can make completely thermally linear devices, which you cannot do with semiconductors. And more than anything, what you can do is create low-power devices. Our first technology that was brought to market a few years ago uses 1,000 times less energy than a silicon device. Imagine if you can get that into every electronic device. You can, because that's an inherent property of graphene. It's not a design of our sensor, it's just a property of graphene. So today, we use a standard approach to everything. We use standard semiconductor tools, we use standard processing, we use all of the steps that you would see in a silicon fab, but we use graphene. So we have a semiconductor process, we have semiconductor equipment. If anyone from a fab came and walked into our facility right now, they'd go, oh, I know that piece of equipment, I know that piece of equipment. And that's the key, integratability. So we're now at a point where we can provide wafers of devices, where we can use standard design tool sets, standard architectures, but we can take the silicon away and we can put graphene in its place, which means we can then utilize the properties of pure graphene. Once you've done that, everything downstream becomes the same. So we deliver standard devices. We deliver standard packaging. We have OSATs that work with us out in Malaysia that work with standard semiconductor, OSATs were outsourced assembly and testing, which are companies that do the back-end assembly for you. They use our devices. They see no difference in packaging our devices and testing our devices than you do from a standard silicon device. So we're integratable. And today, this means we can start to create devices that are truly revolutionary. That device on the screen there, I have one in my pocket just to prove that it's real. They do exist. That's not been made up. That device there is a solid-state molecular sensor. So this is using a standard, you will have seen it in literature, you'll have seen it in labs. We're not claiming to be the inventor of this type of technology, but we are the company that's scaling it. So this device here is able to detect chemical and biological agents, whether that's bacteria, whether it's viruses, whether it's gases, is able to detect those things within 5 seconds. So you remember you had COVID sensors early in COVID. Does anyone remember that far? Where you had your LFT tests, and then if you really wanted to get a good result and you really wanted to test, you would send it off to a lab for PCR. And the reason for that is that PCR testing is more sensitive, can give you a much better certainty of whether you have COVID or not. This device is more sensitive than PCR. So you can put it in your hand, you can take it with you, you can have it in your home, you can test, and within 5 seconds you'll have a better result than you would by sending it to a lab. Why is that important? Because one of the biggest problems in the medical industry right now The biggest carbon footprint of the medical industry is transportation of samples to labs. So all of a sudden you now have a point of use sensor that you can use and test. You have none of that carbon footprint. So this is how electronics made of graphene, not just on the power side, but on the application side, can start driving towards net zero and helping industries and helping application spaces get towards their goals for net zero as well. Today, and in fact in 4 weeks' time, you will be able to access a graphene foundry. So anyone in this room can come to us and they can ask us, shall we look at this device? Would you like to work on this device? Would you like to look at how we can put graphene into our device designs? And we are doing that right now. One of the world's largest telecoms companies is working on a device with us right now for next generation RF. That's to replace in your mobile phone currently the 60 to 80 filters you have with a single graphene filter, reducing the power consumption of those filters by up to 80 times. And basically making your battery last longer. So a graphene foundry will exist, graphene electronics foundry will exist for the first time in the world, and it'll exist here in the UK. The plethora of application spaces that's available to graphene is just, well, it's in literature. You can pick up some of the great reports that have been written by the community from around here about the applications that you can use graphene for. But today we have sensors. We've launched 2 sensors. We have a magnetic field sensor and we have a molecular sensor. And the industries that we're putting them in right now are from everything from the electrification ecosystem, whether it's battery manufacturing. We're working with the largest battery manufacturer in the world right now. We're on site with them today, giving them applications where they can test their batteries in less than an hour, whereas they normally test them in 2 months. We have our sensors in new MRI systems. This is taking a magnetic field sensor that's so much more sensitive that you can reduce the power of the magnets in MRI, making the cost of MRI plummet and making it accessible to everybody. We have sensors going into satellites. We have our molecular sensors going into not just medical applications, but things that you wouldn't even think about. We've just seen a problem with food manufacturing and the outbreak of, well, unfortunately, has resulted in the death of somebody, the outbreak of disease because of the contamination of salads. We are putting detectors into the food manufacturing chain to make sure it's safe and to speed up the manufacture of food as well in certain locations. So graphene is now not just removing energy consumption, lowering the amount of requirements that are required in industries, but enabling new applications. All of a sudden we've got properties that we can use that were never available in solid-state devices before, which is making people go, oh, wait a minute, why can't we do this? Or why can't we do that? So to just link it back to the NGI, where is it we're going to go with this? Well, actually, the world's the oyster now. We have the ability to build electronics out of graphene. So the question is, can we do some of the things on the screen? Can we make faster transistors? Yes, we can. Paragraf has made a transistor out of graphene. Can we do the bendable phones? Well, it's all possible. It's all about imagination now. What can we build in this foundry? And what would you like to build in this foundry? It's an open access. So over the next few years, we will be bringing more and more graphene electronics to this world. And what does that mean? Well, all of those stats that can potentially be a problem for us in the future, if we had graphene in some of those chipsets right now, we could reduce that 20% of the world's power consumption by 50%, saving the world 10% of its energy consumption simply by changing material. It's astonishing. But of course, we're tied up into the old materials of silicon, the old materials of compound. We now need to move to that 2D world. We need to start harnessing the properties of these materials in order to bring these new technologies to light. So what's next for Paragraf? We're now going through certified high-volume manufacturing for 2 customers in Asia. So this is talking about building them millions of devices per month. We're also going through complete integrated solutions. So having electronics on the back of those devices, which is the next step to being able to just have plug and play in systems that people are buying. We have graphene-based heterostructures. I mentioned at the start, we've got people who are bringing structures to us, and we're applying graphene as one of the layers in those heterostructures. But actually further than that, although we're called Paragraf, we are not just focusing on graphene. We have other two-dimensional materials that are being developed right now. And actually, we are now probably the only company in the world that can make wafer-scale boron nitride. So having those materials means that we can then start thinking about combining those materials, and we can start creating new types of heterostructures. Instead of using the architecture that we have at the moment for silicon and thinking about putting graphene into silicon devices, why not start thinking about architectures that work for 2D materials and start building technologies around the material as opposed to trying to put your material into the technology? And that's really exciting. Over the next few years, we will see this happen, and it will be brought to life in the foundry that's just about to open up near Cambridge. So, thank you very much.
Thank you, Simon. Very insightful into electronics devices around graphene and 2D materials. Any questions for Simon, please?
Simon, we've met before the Investment Society, and back in 1988, I introduced flash memory to you. What horrible thought, seeing that number, and worked with ASIC technology, but you talked about imagination. And I'm thinking, have you talked to any flash companies about trying to make flash memory
It's a very, very pertinent question, thank you. One of the real ways in which graphene can help AI is raised temperature memory. So yes, we are looking at the moment. One of the issues you have in AI chips at the moment is the localization of memory to be able to reduce that latency. And so there's an issue if you use silicon, because the thermal drift causes a problem, causes an error state. Graphene with its linear thermal coefficient means that we can start bringing new memory solutions. Yeah, so yeah, definitely something we're looking at.
Some quite interesting research in the NGI around step logics as well, which all fits in with these designs, so quite interesting to talk to you. Sorry, yes.
Thanks for the talk, Simon. You mentioned power semiconductor, 1,000 times less power.
Mm-hmm.
Could you elaborate on that? Where in the chip do you get the gains?
So it's mainly down to the, I've got to be a little bit careful what I'm about to say because we're patenting something at the moment, but it's really down to the switching voltages that you can use when you're using graphene, or when you're using two-dimensional material heterostructures. I won't say any more about the materials in that. But yeah, it's about the on-off voltage that you can use, and it's also about the cooling as well. So by having graphene in chipsets or having graphene in logic, you don't need as much cooling, because I didn't touch on it there, but graphene has a fantastic thermal coefficient as well. So you reduce the amount of power. I mean, data centers right now, the main use of power is cooling. And so you can lower that as well at the same time. You end up with this huge energy gain.
Can you deposit on 300 millimeter?
Yes.
Good.
Just talk about all the benefits except cost. So how does it compare?
I don't know, are there any investors in this room?
All semiconductor is cost effective when you look at the volume markets.
So that's exactly it. The reason I talk about integratability is that we cannot grow a market if we're not competitive in price. So the whole reason for pushing using silicon tools and silicon processes and silicon approaches is to have that cost effectiveness.
Do you have it like at scale? Is there a threshold? Like if you go to TSMC, you would ask, they have a MOQ. What is your MOQ?
So TSMC is an interesting question, because TSMC are trying to patent graphene as well now. I don't know whether you've noticed. But at the moment, I can't talk about price.
Okay.
Because, as you can imagine, we're a value sell at the moment, not necessarily a volume sell.
Any more questions? Thank you very much, Simon.
Thank you.